Okay, hi. So this is lecture on queuing analysis, which is chapter 13 on the textbook. And this lecture or this topic will involve a lot of formula, but I don't expect you to memorize any of the formula. It's just important that you know, like when you read certain cases, and you need to be able to identify whether these cases is under which category. Okay, so we are going to talk about a few waiting line systems. The first one is the single server waiting line systems, and then we also have undefined service time, and we have constant service time. They are related, but there are difference between the two of them. And we have finite queue length and finite calling population, and we have a multiple server waiting line, and we are also going to discuss some additional types of queuing system, but the main system is this one from 13.2 until 13.6. so there's actually a set of formula for each set of for each type of waiting line system, but it is important that you will be able to identify when you read a certain cases, you know that okay, so this is a single server waiting line system, this is this is multiple server waiting line system, and etc. Okay. All right, so before we begin, we are going to talk a little bit of the elements of waiting line analysis. So as an overview, a significant amount of time spent in waiting lines by people, by products, okay, and etc. Like when you go to the airport, then the aeroplane is waiting, there must be some queuing, waiting to take off. And then there will be like when you go to the store and you have already choose certain things that you want to buy, and then you go to the counter and then you have to wait. And then at the clinic, at the hospitals, so these are the examples of the waiting lines. Okay, and the waiting lines is not just people, like people going to hospital, people going to the clinic, but it's also, we can analyze waiting lines by products, like in the manufacturing plants. The products that we produce in bulk, and they're waiting to be processed in the next machine, and so on and so forth. So providing a quick service is an important aspect of quality customer service, because what does it mean by a quality customer service is that when people, or when the product doesn't have to wait so long to get served. And the basis of waiting line analysis is the trade-off between the cost of improving service and the cost associated with making customers wait. So you must have some experience of going to the bank, for example, and then many of the counters are not even open, and you have to wait like a significant amount of time. And you know that if the bank want to serve the customer better, they would provide more counters and they would provide more staff. But providing more staff and providing more facilities will incur the cost of services. Okay, but at the same time, if they want to reduce the cost of staff and the cost of services, what happens is that they might face another cost, which is the cost of losing the customers, because you might not be willing to go to the same bank anymore, and you might open you might put your deposit in another bank, because you say that, okay, this bank I have to wait for very, very long, and I don't want to waste time, and you put your deposit in another bank. All right. So the queuing analysis, which we will learn in this topic, is the probabilistic form of analysis. So in the previous classes, we have covered the deterministic analysis, which is the linear programming, where you know for certain the price and the cost of a certain thing and the demand of a certain thing. But when we talk about queuing analysis, this is related to probability. And the results of the queuing analysis is what we call as operating characteristics, and this is what we want to compare. Like for example, when we do queuing analysis is when we want to study whether the queuing system in a certain store or in a certain manufacturing plant is okay. Are they okay, or are they like underutilized, or are they overutilized? Okay, is the queuing system so far is okay? And what we are looking at is actually the operating characteristics. So the results, or these operating characteristics, are used by the managers of queuing operation to make decisions whether they want to increase the number of staff, which will involve some cost, or they want to they want to add another counter, they want to improve their services and so on. Now let's look at some of the elements of the waiting line analysis. So waiting line forms because there are people or their products arrive at a service faster than they can be served. Like for example, if a customer come to the store every 5 minutes, okay, and the cashier there's only one cashier, we are talking about small store here, and the cashier is able to serve this customer within 1 minute, yeah. So because the service time is actually lesser than the arriving time, so there will be no queue, because as the customer come in, they will get served immediately and then they go on off, and then another customer come in, they get served, and then they're being served and then they gone off. So waiting line forms because people or things arrive at the service faster than they can be served. So most operations have sufficient server capacity to handle customers in the long run. We believe so, because otherwise the queue will get longer and longer and longer, and once you'll never be able to serve all the people or all the products. Customers, however, do not arrive at a constant rate, nor are they served in an equal amount of time. Okay, so when we just take a very, very simple example here at the counter, at Tesco counter. Okay, so the customer sometimes they come in bulk. Okay, they can come in the largest number of customer may come in during the afternoon, and then very, very small number of customer, relatively small number of customer come early in the morning or very, very late at night. Okay, so they don't arrive at a constant rate. Okay, and they also don't getting served in the equal amount of time, because sometimes you buy more things compared to another customer. So waiting lines are continually increasing and decreasing in length, but in the long run it approach an average rate of customers arrival and average service time. So we can take like in one day, okay, how many customers coming in and how many what is the average time that they're being served. So you can take this approach of an average rate of customers arrival and the average rate of the service time in the long run. And the decision concerning the management of waiting lines are based on this average for customer arrival and service time. And this average are used in formulas to compute the operating characteristics of the system, which in turn form the basis for decision making. Right, so now let's talk about the single server waiting line system. And in the single server waiting line system, we assume that in the store or in the manufacturing plant, whatever it is, okay, so there is only one queue line and there is only one counter. There's one service counter. So the components of a waiting line system include the arrivals, which is the customer arrivals, and also the server, which is people at the counter or the machine that do something to the products. And also the third components is the customers in line form a waiting line. Okay, so there are several factors to consider in analysis. The first one is the queue discipline, and number two is the nature of the calling population, and the third one is the arrival rate, and the fourth one is the service rate. Now let's talk about each of this. Yeah, so imagine this is like showing some pictures. So this is like customers arriving at the fast shop market, and they are forming one line here, and there's only one server, and customers keep arriving, and then those who have already choose something, they are forming a line to be served. So now let's talk about each of these disciplines. Yeah, each of these components definition. So the first one is the queue discipline. The queue discipline is the order in which the waiting customers are served. Okay, alright, I'm not sure whether it's been discussed here, but okay. So the queue discipline, there are basically four types of queue disciplines. Yeah, but we take it as first come first serve. So if you are the first coming to the counter, then you will get served first, and then the second person will have to wait for you, and then the third person will have to wait for the second person, and so on. But there are many queue discipline. Like for example, if you store something in the vending machine, for example, yeah, so it's like first come first out. Yeah, so if this bottle goes first into the machine, and then you put it further at the back of the vending machine, and then you put the last bottle in the front. So when people is going to buy the product, the last one that comes into the vending machine will be purchased first. So that is like first come last out. Yeah. But the queue discipline that we talk most in this topic is the first come first serve. And then we are talking about the calling population. The calling population talks about the source of the customers, whether it's infinite or it's finite. So infinite means that like for example, like the Tesco shop, yeah, Tesco hypermarket. You'll never know, even though you can observe on daily basis like how many customers coming in, but the customers can be anyone at all, anyone from the whole world. Yeah, anyone can go there. So there's no like a limit on the population that goes to Tesco. But sometimes the population is also finite. Like for example, we are talking about the Klinik Kesihatan Pelajar, yeah? the university clinic. So the population is finite up to the UM staff and UM students only. So for example, how many UM staff and how many UM students we have, like certain thousand numbers, right? So there is a finite calling population. So people other than UM staff and UM students are not allowed to go to the hospital, to the university clinic. Okay, the students clinic, I would say. And then the third component is the arrival rate. This is the frequency at which the customer arrive at a waiting line according to a probability distribution, and we assume that the arrival rate is distributed using Poisson distribution. And then finally is the service rate. So the service rate is the average number of customers that can be served during a time period, and this is often described by the negative exponential distribution. So this distribution are different, yeah, the Poisson distribution and the exponential distribution. Okay, now let's talk about the first model, which is the single server model. So there are a few assumptions on the basic single server model. If one of these assumptions is not met, then you are not able to use the formula for the single server model. So the first assumption is an infinite calling population. Means that the example of Tesco, yeah, you'll never know who is coming, you know, there's no limit on the population. And then it assumes a first come first serve queue discipline, and then the third one is the arrival rate is assumed to be distributed Poisson, and the service time is exponentially distributed. So we use the lambda symbol for the arrival rate, okay, and the arrival rate is actually the average number of arrival per time period. Okay, it can be within 1 minute or within 1 hour or within 1 day, 1 year, okay, doesn't matter, but this is the average number of arrival of customer or of a product within a specific time period. Same goes to the service rate, which is represented by mu, and this is the average of number being served or per time period. So the customers must be served faster than they arrive, or the lambda must be less than mu, or an infinitely large queue will build up. Alright, so now let's look at this formula, and this is the formula for the single server queuing formula. First is the probability that there will be no customers in the queuing system is given by P naught, and this is PO, yeah, PO or P naught. And this is the formula 1 minus lambda per mu, and then the probability that n numbers of customers are in the system is given in this formula, and then L is the average number of customers in the system, and LQ is the average number of customers in the waiting line. Even though the number of customers will fluctuate on daily basis, yeah, like for example, if you go to the hospital, a lot of the patients are actually waiting very early in the morning. Like this is, I'm talking about PPUM, yeah, the university hospital. A lot of customers, a lot of patients are waiting very early in the morning, and then the number reduce, and until the afternoon the number is like much smaller compared to earlier in the morning. And then they have the second sessions in the afternoon, but the number is not as great as in the morning. But we are talking about the average here. So on average, doesn't matter the time, what is the average of the numbers in the system and what is the average of numbers in the waiting line. So the difference between this in the system and in the waiting line is that in the waiting line is just the number of patients queuing to be served or queuing to meet the doctor. They haven't met the doctor yet. But when we are talking about customers or the patients in the system, in the whole system, it includes those who are currently meeting the doctor. And then we have the average time the customer spends waiting and being served. So this is like the average time the customer spend in the whole system, like how many minutes or how many hours are they waiting, including the hours they are being served. And then WQ is the average time the customer spend only in waiting in the queue. Okay, so WQ should be lesser than W and LQ should be lesser than L. And then we also have U. U is the probability that the server is busy. Okay, so on average, whether this server is busy or not, and the maximum number is also is of course 1. Yeah, and then the probability that the server is idle is given by I, which is an inverse of U. So now let's look at this first example. Yeah, so we are talking about a fast shop market here. So we only have like one queue line and we also have like one server, and the arrival rate is 24 customers per hour arrive at the checkout counter, which means that within 1 hour 24 customers arrive, and within 1 hour 30 customers can be served. So this one you can see that lambda is lesser than the service time. Lambda is lesser than the than mu, which means that in the long run we are able to clear up all the queue. Now to compute the P naught, yeah, the probability that there's no customers in the system is given by P naught. So I'm just following all these formulas, so you can take the time to pause the video and then you can go to Microsoft Excel. So this is what I do. For the first case is the single server, so I put in lambda and mu, and then I just put in the number 24 and 30, and then first is we compute the P naught. I think this is very straightforward, so you just follow the formula. So P naught is given by 0.2, which means that the probability that there will be no customers in the queue is given by 20%. So 20% of the time there will be no customers in the queue. And then L, where on average how many customers are in the system. So on average there are 4 customers in the system. So you just follow the formula and you just plug in the formula. And then this is LQ, and LQ is 3.2 customers on average is waiting in line. And then W is how many customers are waiting, how many hours or how many minutes the customer spend waiting in the system. Okay, so it's given by this one. The formula is given by 1 divided by mu minus lambda, which is 1 divided by 30 minus 24, and I just multiply with 60 because I want to know in terms of minutes. Yeah, so in terms of hours you might get 0.16 hours. So and then we convert into minutes times 60 minutes, you get 10 minutes. So we can say that in average the customer spend 10 minutes in the system, which is I think quite okay. Yeah, I'm not sure about you, but yeah, waiting for 10 minutes probably okay. And then WQ is the average time the customer spend in the waiting line. It is 8 minutes. But if we consider if this is a very small store like 99 Speed Mart, and then you're waiting for 8 minutes, I think it's quite long. It depends on the context as well. And U is the utility that the server is busy. Server means the counter. Yeah. So the probability is given by 0.8, and of course I is 1 minus U, which is 0.2. So in this case 20% of the time the server or the people at the counter, the cashier is free, but 80% of the time they are busy serving the customers. So looking at this in terms of utilization, I think is quite okay, but in terms of the waiting time, that you spend like 8 minutes waiting in the queue and then 10 minutes in the whole system, some people might find this like, okay, this is quite long for a very small store. Okay, all right. So the steady state operating characteristics. Because of the steady state nature of operating characteristic, the utilization factor U must be less than 1. Okay, so here if U is less than 1, it means that the formula for U is given by lambda divided by mu must be less than mu, and mu must be less than 1, and so lambda must be less than 1. So this means that if it is larger than 1, then you're going to develop a very long and then a very long queue that will just add up, and you will never be able to clear up the queue. So the ratio of the arrival rate to the service rate must be less than 1. In other words, the service rate must be greater than the arrival rate, and the server must be able to serve customers faster than the arrival rate in the long run, or waiting line will grow to infinite size. So I'm just going to check whether everything is okay. Alright, so what is the effect of this operating characteristic? So all the P0, all the L, LQ, W, WQ is what we call as the operating characteristic, and these are the numbers, and this is the characteristic that we want to use in order for us to make decision. So a manager wishes to test several alternatives for reducing customers' waiting time. Number 1, okay, maybe they think that 10 minutes spent in the system and 8 minutes spent in the queue is very long, so they want to do something, and but doing something and increasing the service will add the cost. So they are thinking whether or not they want to pursue these alternative plans. Now let's look at this. Yeah, so the first alternative is they want to add another employee to pick up purchases. So you still have one counter, but instead of just having the cashier to do everything, they want to add another employee to put everything in the plastic, or to pack up the purchases, and then the service time will be faster. And then number 2, they want to add another checkout counter. So now we are having 2 checkout counter instead of 1. So now let's look at the first alternative. Yeah, by adding another employee to help with the packing, they can raise the service rate from 30 to 40, which means that instead of serving 30 customers in an hour, they can serve 40 customers in an hour. But it costs an additional $150 per week. However, they can avoid losing $75 per week for each minute of reduced customer waiting time. You imagine at Jalan Bukit, for example, there's 99 Speed Mart and there's KK Mart, right? And like a lot of people actually going to 99 Speed Mart, and then they have to wait like 10 minutes. They have to wait 10, 8 minutes, and then you see, oh, KK Mart is empty, I better go there. So the cost of losing these customers is actually estimated to be $75 per week for each minute of reduced customer waiting time. Okay, so now let's look at this updated operating characteristic with the new parameters. So I just put here everything here. Okay, so this is the original one that we have discussed before, and then looking at the first alternative, the only changes is actually here. Instead of 30, now we can serve 40 customers, and then with an additional cost of 150. So now we look at the difference between these two. Yeah, so you can see the waiting time is actually reduced from 10 minutes to 3.75 minutes. This is like a huge reduction. But look at the waiting time in the queue. It has reduced from 8 minutes to 2.25 minutes. So you're waiting for 2.25 minutes. There is like little chance that you will go to another store. Yeah, because 2 minutes is not that long. So now let's look at this, and then we look at the cost. Yeah, so the time saved is 8 minutes minus 2.25 minutes. So you already save 5.75 minutes, and this 5.75 minutes you multiply with $75 because you save $75 for each minutes that you can save from your customers. So the cost save is $431, but you need to pay for the additional employee, which is $150. So but still the total saving is positive. Yeah, so this one is 431 minus 150, you get 281. So you're still able to save, even though you think that, oh, I'm going to have to pay, because the $75 you don't really see it's coming into your pocket, but actually you are retaining customers, and retaining customers is one important concept in business. All right, now let's look at the second alternative. The second alternative says that instead of having a new employee to help with the packing, you add another checkout counter, but this one will cost you $6,000, plus you need another person to work on the second counter, plus you need to pay $200 per week for additional cashier. Now let's see whether this is a better alternative. By having this, you are actually dividing the arrival of the customers into 2 checkout counters. So originally you have 24, the arrival rate is 24, you divide by 2, so you have 12 for each of the counter, and the service is still the same because each of the counter can still serve the 30 customers per hour. Now let's look at this updated operating characteristics. So the difference is here, and I just copy everything. I don't have to retype everything, I just copy whatever is in the original one. I just put it here. Now we look at WQ. So originally it was 8 minutes. By adding a helper, you can reduce to 2.25 minutes, but by adding another checkout counter, you reduce to 1.3 minutes. So 1.3 minutes, it's very, very huge reduction. So because you are able to save, you're able to save 6.6 minutes, and we multiply this with $75. So 75 times 6.667, you get 500. And then this 500 you need to minus 200, because every week you need to pay this new employee and the new counter with 200. So actually you are able to save $300 per week. But for the first few weeks, like imagine if you are like you have to clear up this $6,000, because to get the new counter you need to pay $600, right? $6,000. So $6,000 divided by 3,000 that you are able to save here. Divide by this, you get 20 weeks. So for the first 20 weeks you are not able to get anything, but after 20 weeks, you are able to get 300 is actually larger than 281. So compared with the first alternative and the second alternative, the total saving for the second alternative is actually higher, except for the first 20 weeks. So you might also want to consider that as well. So many things that you want to consider. Number one is that in terms of the waiting queue, of course the second alternative is actually lower, even though between 1 to 3 minutes and 2.25 minutes, I'm not sure. Some people might find it this is significant, but some people might say we just better use the second alternative. It depends on the context. All right, and now let's look at this. This is the summary, and of course there's a cost trade-off for service level. As you increase the cost of the services, the service time will go down, and the cost of waiting will go down. But at the same time, you need to find some point in which the service level to maintain is actually minimizing all the cost. So this is the Excel. All right, now let's talk about these two. So the first one is the constant service time, and the second one is the undefined service time. So we talk about the undefined first. Let me see. Are we going to talk about the constant first or the undefined first? I think we're going to talk about the constant first, yeah? So the constant, rather than exponential distributed service time, it mainly occurs with machinery and automated equipment. Like, you know, imagine this product is waiting in the queue to be served, okay, to be processed by the next machine. And the service time of this machine is actually constant. Like whenever it fills in the cup or it fills in the bottle, it just take like 3 seconds, for example. And it is constant because we are not talking about human being here. There is no variation. Yeah, this is machine. So now we are dealing with the constant service time. And the constant service times are a special case of a single server model with undefined service time. So the queuing formula for the undefined service time model is given by this. So I'm not going to read all this formula, yeah, but it's adequate that you know. Okay, so this is the formula. You can refer to this formula and then you can do the calculation in the Microsoft Excel. That is what I did for the last hour. You know, I just did it myself. I look at the formula and then I just, type and all that. Okay, so now let's look at this one. Okay, it is quite confusing even for me. Yeah? Okay, this is undefined service time. We're going to talk about the constant service time later, but now we are talking about the undefined service time first. Okay, so what does it mean by undefined service time? So let's look at this example. We have a single fax machine and the arrival rate of 20 users per hour. Okay, so the arrival rate is Poisson distributed, but the service time is undefined. It has a mean of 2 minutes and the standard deviations of 4 minutes. Yeah, so on average it can fax within 2 minutes with the standard deviation of 4 minutes. Now just plug in all this information into this formula. Okay, you just use this formula. So I'm going to show you how I did it. So this is the undefined. So first is we have the lambda, we have the mu, and the mean is 2 minutes and the standard deviation is 4 minutes. But I don't know, for some reason I look at the formula, it use hour instead of minutes. Yeah, so make sure that if you're just using hour, just use hour all the way. If you use minute, then just use the minute all the way. Okay, otherwise there might be some errors in the calculation. So this one is I divide by 60 minutes, I get 0.033, and the standard deviation also 4 divided by 60 minutes. So this is in terms of hours. And then I just plug in all this formula, and this is what I get. Okay, all right. And now let's look at the constant service time formula. So what is the difference between constant and undefined? Okay, so undefined, it has a mean and it has a standard deviation. But constant means that there's no variability at all. There's no variability. If 2 minutes, then it's 2 minutes. It's not like 2 minutes plus minus a certain errors. Okay, so in this case, because there's no variability, then sigma is equal to 0. You remember this one? In the case of undefined service, you have a standard deviation of 4 minutes, but in the constant, this standard deviation is equal to 0. There's no variation at all. Okay, so because the standard deviation is equal to 0, so LQ, if you substitute the variance equal to 0, then the formula will be different. Okay, but it doesn't matter. I'm in the Microsoft Excel, I'm still using the undefined service time for the constant service time. It's just that I changed this to be 0 instead of 0.066. Yeah, I changed this to be 0 and I copy everything, and this is what I get. Okay, so again, this one I just plug in all the numbers into the formula and just type in the formula, make sure that you get the same. Yeah, and let's look at the example for this one. The car wash servicing one car at a time with a constant service time of 4.5 minutes. See, there are 2 clues given here. Number one is that it says that the service time is constant, and number 2 is that they're just giving the mean without the standard deviation or the variance. So the arrival rate of the customers is 10 per hour. So we want to determine the average length of waiting line and the average waiting line. Okay, so we just plug in all this information, and okay, we get this is LQ. Okay, this is L, this is okay. First we look at the LQ. So LQ is 0.139, and then the second question is asking about WQ. So on average, the customers or the cars is waiting 6.84 minutes. Okay, all right. Now let's go to the next one. I think you need to pause once in a while, and then you just work on the Microsoft Excel. Okay, and then we are talking about the finite queue length. Okay, what does it mean by finite queue length? So in a finite queue, the length of the queue is limited. For example, like you're servicing a car, for example, in the car service, right? So the place is quite limited. So you only have like 3 parking spots, and after the 3 parking spots, there's no more spots available. So if the customers keep coming, you have to say like, I'm sorry, but our shop is full, you know, you can go elsewhere, or you can come back later. So that is the example of the length, when the length of the queue is limited. So the operating characteristic, where M is the maximum number in the system. So let's say you're servicing 1 car and you have 3 parking spots available for waiting. So in total you have 4 cars in the system. Okay, number of those who are allowed to wait, and including the one that you are currently servicing. All right, so in this case, these are all the formula. The formula is getting you know, crazy as we go, and the hardest one is L. Okay, this one, let me show you. Yeah, this is finite queue length L. Yeah, finite queue length for L. So this is like, that is how long the formula can go, but you have to do it correctly, and then you have to check whether your answers is similar to the one in the lecture notes. Okay, and let's look at this one. This is a single base service. They have space for 1 vehicle in service and 3 waiting for service, and the mean time between the arrival of customers is 3 minutes, and the mean service time is 2 minutes, and both inter-arrival time and the service time are exponentially distributed, and the maximum number of vehicle in the system equals 4. So M is equal 4 in this case, and this is when you have to be careful. Okay, the arrival time is, okay, the arrival rate is not 3 and the service rate is not 2. Don't take it straight away, okay, because you need to know that the arrival rate is the number of customers arriving within a time period. So if you are talking about the hour here, so how many customers arrive in 1 hour? If 1 customer arrive every 3 minutes, so in 1 hour, okay, 60 divided by 3 is 20, so 20. So the lambda here is not 3 but lambda is 20. Similar to the service time, if each customer gets, you know, being served for 2 minutes, which means that in 1 hour you can serve how many? 60 divided by 2 is 30 customers. So the mu here is 30. Be careful with this, yeah. If you put 3 here and you put 2 here, then everything else will be wrong. Okay, so these are the formula, and then you just follow all the formula, and then this is the finite queue length. Yeah, I got this, and alright, I think that's all. Yeah, you can tell that, okay, on average there are 1.2 customers in the system. On average the customer wait 0.06 hours in the queue, and etc. Right, now I would like to talk about the finite calling population. Okay, the difference between finite queue is the queue is limited, But finite calling population is when there is a limited number of potential customers that can call on the system. Like for example, if you're a teacher, you're teaching a class, one classroom, okay, and you have like 20 students in your classroom, and then at the end of the year you are making appointments with each of them to discuss about their progress and etc. So there, in that case, you have a finite calling population. You only have like 20 students waiting to meet you, okay. So the operating characteristic for a system with Poisson arrival and exponential service time is given by, okay, the P naught, which is the probability that there's no customers waiting in the system, is given by P naught. And to do this, you see that it involves like factorial and it involves some summation. So in order for you to compute this, so you have to do it like one by one, okay. This means that N, the capital N, is the population size. So let's say if there are 20 students in your finite population, then N is equal to 20, and you have to run this 20 times, yeah. So this means that 20 factorial, okay, you start from N equal to 0. So you start with 0 factorial divide by 0 minus sorry, this is capital N. Capital N is 20, yeah, in the case of if your N is 20. So 20 factorial divide by 20 minus 0 factorial, okay, times lambda divided by mu to the power of N, and current N is 0. And then you have to plus 20 factorial divide by 20 minus 1 factorial multiply with lambda divided by mu to the power of 1. And then you go to 2, n become 2, and n become 3, 4, 5 until 20. And then you have to take everything and you have to get 1 divided by the summation of all that, and then you got P naught. So this is quite a long process actually. If you do this using your calculator, then I don't think you will be able to, especially if n is very large, yeah. So that's why I'm using Microsoft Excel, and this is how you do it. This is actually explained in the lecture notes as well. So you put n is from 0 until 20, there 20, and for each of this you take factorial of 20 divided by factorial 20 minus, first you start with 0 and then multiply with lambda divided by mu to the power of 0, and then you go to 1, to the power of 1, and so on. And finally you add all this, okay, you add all this. This is the sum of everything here. You add, and then to get the P naught, over here, you just take 1 divide by the sum of what you got here, okay. And then the P naught is given by 0.64, or 65% of the time the system is busy, okay. And then the rest of this, I think, is not that difficult. It's just, the formula is not that difficult, so you just follow the formula, and then you get all the operating characteristics given in the Excel. So everything that I got here is actually more or less same to the number that in the lecture note, yeah. So you can just use this formula and then see if you get exactly the same. So in this case, we are talking about Wilco Manufacturing Company. They have 20 machines, yeah, and this is their finite calling population. N, capital N, is equal to 20, and each machine operates on average 200 hours before breaking down, and average time to repair is 3.6 hours. So the breakdown rate is Poisson distributed, and the service time is exponentially distributed. So this one also, the arrival and the service is given in terms of the time, and you need to convert this, yeah. So if the machine is broken down, they break down every 200 hours. So let's say within 1 hour, how many machines are broken down? So it's given by 1 divided by 200, which is 0.005. And then the service rate, okay, so the time taken to repair is 3.6 hours. So in 1 hour, how many machine got repaired? Okay, so this is like 1 divided by 3.6, you get 0.2778. So it's like 0.27 machine being served in 1 hour. And of course the capital N here is 20 machine, the finite calling population. So the P naught here, okay, this is a very long process that I've shown you in the Excel just now, yeah? And then the rest of it, you just plug in all the numbers, and then you get this one. And now let's look at this one, yeah? So the machine needs to wait almost 2 hours before they are being repaired. And I would say that this is quite a long waiting time, yeah? And in fact, they spend like 5 hours in the system to be repaired, including the repair time. Imagine you are running something, you know, and every 200 hours one machine break down, and you have 20 machine, all will break down every 200 hours. So imagine what happened to your, you know, your manufacturing, what is this, yeah, manufacturing company. So what happened to the manufacturing plant if the machine spend like 2 hours waiting, and then 5 hours, 5.5, over 5 hours waiting in the system? You can't use this. Okay. And then finally is the multiple server waiting line. So in this case, you still have one queue, okay? We're not talking about multiple queue, multiple counter here. You still have one queue, but everyone will go to the first available counter. Like, let's say there are 3 counters, so you just wait in one queue, and then when one counter become available, you go there, okay? And the next person will wait for the next available counter. It might be counter 1, 2, or counter 3. Okay, so now let's take this example from the big department store service department, and it assumed the first come first serve basis again. And this is the assumptions, yeah? First come first serve, Poisson arrival, exponential service time, and infinite calling population. Similar with the single server, except that we have like multiple server. So the parameter definition is the lambda is the arrival rate, mu is the service rate, and C is the number of the server, or the number of the counter. Okay, and the mean effective service rate for the system is given by C times mu, and this must exceed the arrival rate. And this is the formula, and I would say that the hardest one is actually P naught, but not that hard, not like the previous one. So now let's take this example where the arrival rate is 10 and the service rate is 4, and there are 3 counters, or there are 3 servers. And first we want to compute P naught, yeah? So this is how you compute P naught. Let's say C is equal to 3. So you start with n equal to 0 plus n equal to 1 plus n equal to 2, because you have to stop at n equal to C minus 1 over here. Okay, you have to stop at C minus 1. 3 minus 1 is equal to 2. So not that lengthy. So what I do is that with the 10, 4, and 3, so you just plug in into Excel. Okay, 10, 4, and 3 over here, and here I put C mu equal to 12. And then first is we compute the one in the this function, this summative function first, yeah? This one. I just compute this part only, okay, this part only. So this one is given by, okay, this formula, and I compute from 0, 1, and 2, and then I compute the sum. So the P naught is given by quite lengthy also, this one. So you just follow all the formula, and then you get, yeah, the L, LQ, WQ, and etc. Okay, so I think, yeah, this one also shows you the formula, so you can follow the lecture notes. Alright, so the questions that will arrive is, first is you are expected to know, like for example, when you read certain cases that is being given to you, you need to know that whether, you need to identify whether this is a multiple server, is this a undefined, or is it a constant. You need to find out. First you need to identify. Once you have identified, then you can just refer to the formula. The formula will be given, you know, the formula wouldn't be like thrown at you without explaining what is this formula for. Yeah, so the formula will be given to you, where you know that, okay, this is formula for multiple server, this is the formula for, you know, finite calling population, and etc. So you just have to use the formula and make sure that the calculations that you do is correct. That's all. Now let's talk about some additional types of queuing system. Okay, sometimes we have single queue with multiple server in sequence. Like you go to the first server and then you have to go to second server and third server, you know. Or you can have a single queue with multiple servers in sequence, like this. So this is some additional type of queuing system that we don't discuss in this topic, but the operating characteristic can be computed in those, you know. And there are other items contributing to the complexity of a queuing system. Number one, system in which the customers balk from entering or leave the line. Okay. Number two, when the servers who provide service in other than a first come first serve manner. So, you know, you choose the customer files at the back to come first. Okay. Or you choose the customers, or you choose the patient based on the severity of the emergency. And then you also have like service times that are not exponentially distributed, or are undefined or constant. And then number four, when the arrival rate is not Poisson distributed. And lastly is the joking. So this one is not included in the consideration. Yeah, joking is when, you know, when you wait. I'm sure you all have done this. Yeah, you wait at this counter and then this counter took very long. And then you see that the other counter actually gets served very fast, so you jump into the next counter. So that's called joking. But what happened is that when you jump to the next counter, that counter become a long queue, and the counter that you left is actually you know, the person who were at your back previously now in your front. Okay, so there's an example problem solution as always for your you know, for you to run and then see if your answer is correct, and that's all.